Imagine taking apart a perfectly functioning classical clock.
Oh, like right on your workbench.
Exactly. You've got it sitting right there on your workbench. You've unscrewed the back plate, and you're looking at all these beautiful deterministic pieces.
Right, the mechanical guts of it.
Yeah, you've got the heavy brass gears, the tightly coiled springs, the little swinging pendulum ticking back and forth.
Very predictable.
Totally predictable. You can see exactly how the kinetic energy transfers from one tooth of a gear to the next. It is a closed, perfect, totally classical system.
And completely self-contained.
Right. And as you're staring at it, you start wondering something crazy. Could I just, swap out a few of these brass gears for quantum mechanics?
Just kind of slide them in there.
Yeah. Could I make this clock quantum? But here's the thing. You have to be totally transparent about what the clock is already giving you and what you are deliberately bolting onto it.
Because you can't just sprinkle quantum dust on a brass gear and call it a day.
No, you definitely can't. And that delicate, strictly honest boundary between what is naturally there and what we choose to build is exactly what we are exploring today for you, the listener.
It really is the core of the whole thing.
Our mission today is unpacking a really dense, fascinating theoretical paper. It's called Addendum 24, Canonical Phase Structure Condensed by John Sermont.
It is the perfect mission for us today, honestly. Because this paper is a masterclass in extreme theoretical discipline.
Extreme discipline, I like that.
Yeah, we are looking at a very specific extension to a framework called the Oscillatory Dynamics Transductive Bridging Theorem, or ODTBT.
ODTBT, right.
Specifically, we are diving deep into how this theoretical framework handles one central vital variable. It's called recursive phase strain, and in the mathematical notation, it is denoted as delta phi.
Delta phi. Okay, before we even talk about recursive phase strain, let's just make sure we're all visualizing the same thing.
Yeah.
Because the goal of our deep dive today is to help you understand the exact, rigorously honest boundary. The line between what a physical theory already gives us the classical foundation and what we deliberately build on top of it.
The quantum extension.
Exactly. So let's inventory the workbench. Before we can build any new quantum parts, what materials are already sitting there?
What's in the box?
Yeah. What does the existing mathematical framework, what this paper refers to as the corpus, actually give us regarding delta phi?
That is exactly where we must begin. So, in the existing ODTBT corpus, delta phi is strictly a classical variable.
Okay.
There's absolutely nothing quantum about it. It behaves dynamically, meaning it is a dynamical coordinate.
So it moves and changes?
Yes. It evolves over time, it reacts to forces, but it does so entirely within the strict, predictable rules of classical physics.
So it's a moving part, like a gear.
It is a moving part. And to understand how it moves, we have to look at the architectural blueprint of the theory. In physics, we often call that blueprint the Lagrangian structure. In this specific theory, it's called the Recursive Scalar Simulation Action, or SRC-SIM for short.
Okay, let's freeze there. Lagrangian structure and action.
It's a bit jargon.
For our listener who might be visualizing our brass clock, what does SRC-SIM actually do? Is it just like a ledger of energy?
That's a brilliant way to put it, actually. A Lagrangian is essentially a master ledger. It constantly calculates the difference between the kinetic energy of a system, the energy of motion, and the potential energy.
The stored energy.
Right. In classical mechanics, systems always evolve in a way that minimizes the total action over time.
Which is just the Lagrangian added up over a path, right?
Exactly. It's nature's way of finding the path of least resistance. Now, within this SRC-SIM ledger, delta phi has a very specific entry.
Oh, what kind of entry?
It has what we call a quadratic kinetic term.
Quadratic kinetic term.
Yeah.
So just like a car speeding up down the highway.
Yep.
The kinetic energy of a car is 1/2 its mass times its velocity squared. The squared part makes it quadratic.
Spot on.
As the speed doubles, the energy required quadruples. Is it just basic inertia like that?
Exactly like that. Delta phi acts like a moving object with inertia. It has a mass-like resistance to changes in its velocity.
So it fights back.
Yeah, it takes effort to get it moving, and once it's moving, it takes effort to stop it.
So it's heady. It's got heft to it in the math.
Precisely. And that heft, that inertia, is governed by a specific coefficient provided entirely by the existing corpus.
Okay.
This is a crucial piece of the puzzle. The corpus gives us a strain inertia coefficient called alpha effective. It's written as a Greek letter alpha with a little f subscript.
Let's give our listener a really vivid image for this. Alpha effective is like a heavy brass dial that is permanently bolted to the side of our clock by reality.
I love that.
The theory dictates its existence. We didn't invent it. It just came with the machine.
That is a perfect visualization. Hold on to that brass dial. Because we have this kinetic term, and because delta phi has inertia, thanks to alpha effective, standard classical mechanics dictates that we can define a conjugate momentum for it.
Right, because if something has mass and velocity, it has momentum, like a swinging pendulum bob.
Exactly.
It's not just where it is, it's how hard it's going to hit you if you stand in its way. What does the momentum of delta phi actually look like in the SRC sim corpus?
It's a two-part equation. The primary candidate for this momentum includes that brass dial, the alpha effective coefficient, multiplied by the velocity of delta phi.
Mass times velocity, just like you'd expect.
Right. But then there's a second piece. There is a velocity-dependent coupling term, which the paper calls chi.
Chi, the Greek letter that looks like an X.
Yes. So you have inertia times velocity plus this coupling factor chi.
And it's
very robust, very complete classical mechanical setup.
It's a fully functioning gear in our clock.
It really is.
Okay, so we have a coordinate, we have inertia, we have a mathematically sound momentum that includes alpha effective and chi.
Yes.
It sounds like a complete working system. So, what is missing?
What is missing is Planck's constant, the symbol h bar. There is absolutely no h bar anywhere in the existing corpus.
Zero. None at all.
None. The framework is entirely unapologetically classical.
Huh.
Even with all these moving parts, the coordinate, the momentum, the kinetic ledger, SRC sim, there is no inherent quantum mechanics.
So it's strictly classical.
Yes. Delta phi is a classical coordinate. To go quantum, to make this system behave like a quantum mechanical entity, something must be ADD.
Okay, so we acknowledge we have no quantum parts. But if I'm a theoretical physicist and I'm staring at this incredibly elegant Lagrangian,
It's very tempting.
I've got an action formalism, I've got a variable with a beautifully defined kinetic term, I've got conjugate momentum. The friction of the concepts here is insane.
Oh, absolutely.
Because it looks exactly like the foundation of a quantum system. The temptation must be overwhelming to just publish a paper saying, hey, look what I found. I did the math and discovered a hidden quantum system inside ODTBT.
It is incredibly tempting. And frankly, it's a trap that many physicists fall into when dealing with complex classical formalisms.
Right, seeing things that aren't there.
That exact temptation is what this paper is fighting against with everything it has. It would be so easy to write a paper claiming you discovered a quantum layer hidden inside the theory.
But it's not true.
No, it is false. The true version is that we supply an extension, draw a clear line, and lay it on top. Every single quantum piece is built, not found. This is a formal extension, not a corpus derivation.
So you found the quantum structure hidden in the theory?
No, we didn't find it. It wasn't there. We built it and overlaid it, and we're explicit that we built it. We are constructing canonical structure and overlaying it on the theory.
Okay.
We are not extracting structure that already existed in the corpus.
Does this prove ODTBT is a quantum theory?
No. It constructs a canonical route. It does not prove the original theory was secretly quantum.
I want to pause and make sure the listener really absorbs the magnitude of that discipline.
It's vital.
Because if you read science news, you see breakthroughs every week where someone claims they derived something profound.
Oh, all the time.
But here, the author is violently rejecting the claim of discovery in favor of construction. Why is that distinction so important? What happens if we don't construct this honest boundary?
Think about the catastrophe of a false derivation. If you pretend a classical variable is intrinsically quantum, if you claim the corpus gave it to you when it didn't, you might spend the next 10 years building a massive theoretical bridge on top of that assumption.
A bridge to nowhere.
Exactly. Then, when you try to test your theory against actual real-world measurements or particle collisions, the math suddenly predicts infinity.
The whole framework collapses because you hid your assumptions.
The genius of Addendum 24 is that it builds a heavy fire door between the classical house and the quantum addition. SRC sim provides the kinetic foundation. The groundwork is there.
But the rest is new.
Right. The quantum normalization, the actual introduction of quantum mechanics, is a formal extension. It's a superstructure we are choosing to build on top.
So we've got our hard hats on. Let's talk about the actual construction project.
Let's do it.
We acknowledge we are explicitly constructing a canonical route, building the quantum scaffolding ourselves. But immediately, if I'm looking at this blueprint, we run into our first major engineering problem.
A big one.
Delta phi isn't just a position variable like x on a graph. It's a phase variable.
And in quantum mechanics, phase variables are notoriously hostile to being quantized.
Hostile. I want to make sure I understand this. If I'm holding a hammer, I want to hit a nail. If we just try to forcefully smash standard quantum mechanics 101 rules onto this classical phase, what pushes back?
To understand the pushback, we have to look at how delta phi appears in the corpus. In ODTBT, we see delta phi sitting inside a sign function.
Okay.
Specifically, it's inside a mathematical construct called the coherent scalar. Because it is inside a sign function, the output is periodic. It loops.
Okay, I'm visualizing a clock face again. The hands sweep around, reading 1 to 12.
Right.
Then they hit 12, and the next number is 1 again. It reads 1 to 12 over and over. That's a periodic readout.
Yes. But here is the critical distinction. Just because the readout loops does not mean the underlying variable itself is a closed loop.
Oh, interesting.
The numbers on the clock face loop, but time itself isn't a circle. Time keeps stretching forward linearly, completely unbound.
So just because the sine function spits out a repeating wave, that doesn't mean delta phi itself is trapped in a circle.
Exactly. The corpus establishes that we have a periodic readout of delta phi,
Right.
but it does not prove that delta phi is intrinsically compact.
Meaning it's not a closed loop natively?
Right. It is not strictly an angle-defined only modulo 2 pi. The sine function just processes it that way.
Wait. Modulo 2 pi. Let's translate that for our listener. 2 pi is a full 360-degree circle in radians.
Yes, exactly.
So modulo 2 pi just means that whenever you hit 360 degrees, you reset to 0, like the clock hitting 12.
Right.
So you're saying delta phi isn't a steering wheel that only spins in a circle. It might be a straight highway, but we're just looking at it through a spinning wheel?
That's a brilliant way to put it. The underlying coordinate could be infinite, stretching from negative infinity to positive infinity. But the sine function acts like a lens that only shows us a repeating loop.
Wow. Okay.
And this difference between a periodic readout and intrinsic compactness is what causes the entire quantum architecture to violently reject naive solutions.
But why? Why can't we just use the standard naive position momentum commutator rule, the bedrock of quantum mechanics? Position and momentum don't commute. Their commutator equals I times h bar.
Heisenberg's uncertainty principle.
Right. Yeah, that's Heisenberg in a nutshell. Why not just plug our phase and our action directly into that same equation and call it a day?
Because if you do that, you slam headfirst into the Susskind-Glogower problem.
The Susskind-Glogower problem.
Yeah.
Let's make sure we have that name down. Susskind-Glogower. Pronounced G-L-O-G hour.
That's right, Susskind-Glogower. If you try to force a standard commutator onto a phase variable, the math doesn't just get messy. It fundamentally breaks down.
How bad is the breakdown?
Well, the naive phase operator cannot be both self-adjoint and satisfy the canonical commutation relation at the same time.
Okay, my brain just threw an error code. Self-adjoint. We need to hack through this jungle for the listener.
Fair enough.
Why does the math break? I'm going to try to invent a workaround, and you tell me why it fails. Let's say the action variable, the number of quantum particles, or quanta, is like a ladder.
Okay, a ladder, a very common quantum analogy.
In most physical systems, that ladder has a bottom rung. You can have 0 particles, you can have 1 particle, but you can't have -3 particles.
Right. There's a ground state, a floor.
Yes. The action must be a positive number. There is a vacuum state at the bottom.
Okay, so if I apply the naive commutation relation for phase and action, the standard quantum 101 rule, what does it do to my ladder? The naive commutator essentially acts like an elevator that must always be able to go up and always be able to go down. The mathematical rule dictates that an infinite shift is always possible in both directions.
But if I'm on the bottom rung of the ladder, if I'm at the ground state, I can't go down anymore.
Exactly. And that is the paradox. When the elevator hits the floor, the mathematical gears strip entirely. The math basically crashes.
Oh, man.
And when it crashes, the operator ceases to be self-adjoint.
And why is self-adjoint so important? Why can't we just lop off the bottom of the ladder? Just write a Post-it note on the mat that says, stop at 0.
Because you can't cheat the foundational rules of quantum observation. In quantum mechanics, an operator must be self-adjoint to represent a real, observable physical quantity.
Okay, what if it isn't?
If it isn't self-adjoint, it means the math yields imaginary numbers, like the square root of -1 when you try to measure something.
Oh, that's bad.
It's fatal. Imagine stepping on a bathroom scale to weigh yourself, and the digital readout says I pounds, or 4 plus I kilograms.
You can't work with that.
No, you can't build a physics theory on a scale that spits out imaginary weights. So when the naive elevator tries to go below the ground floor, the math starts spitting out imaginary results.
So the whole thing falls apart.
Right. The operator cannot be self-adjoint, which guarantees real numbers while also perfectly satisfying that simple naive elevator commutator. It is a famous, immovable paradox that Leonard Susskind and Jonathan Glogower identified way back in 1964.
And it wasn't just them, right? The paper brings up a whole history of physicists wrestling with this exact nightmare.
Yes, Addendum 24 rigorously acknowledges this history. It brings in the Pegg-Barnett analysis.
What's Pegg-Barnett?
Yeah, that's Pegg, P-E-G-G, Barnett. They tried to solve this paradox by working in finite dimensional truncations. They basically chopped the infinite phase space into finite chunks, analyzing it piece by piece to see exactly where the naive math goes wrong in the limit.
Smart. Did anyone else try to fix it?
The paper also references Kastrup, K-A-S-T-R-U-P-P. Kastrup pointed out that the topological structure of a compact angle, when forced to interact with an action that has a hard floor, creates fundamental algebraic obstructions.
So it's basically a known dead end.
Completely. The consensus in the literature of the last 60 years is absolute. You cannot just use the naive phase operator globally. It is mathematically unsafe. It is a bridge that will collapse.
So we have this massive mathematical roadblock. The naive approach gives us imaginary bathroom scales. Smashing the hammer doesn't work.
No, it doesn't.
We are explicitly building an extension, and we need our scaffolding to hold weight. What is the constructed workaround in Addendum 24?
To fix this, we construct a workaround. We don't find a loophole, we build one. We introduce a new operator called U delta. This is an exponentiated unitary operator. Mathematically, it is written as U delta equals e to the power of I times delta phi.
E to the power of I times delta phi.
Okay, we are putting our classical variable delta phi up into the exponent.
Yes.
We're multiplying it by the imaginary unit I and making it the exponent of Euler's number, e.
Yeah.
How does that save us?
Because of the magic of Euler's formula? When you put an imaginary number in an exponent like e to the I theta, or in our case, e to the I delta phi, the math literally draws a circle.
Oh, really?
Yeah. No matter how incredibly large or infinitely small the phase delta phi gets on that straight linear highway, the exponent wraps it around and around a circle of radius 1 on the complex plane.
It's a mathematical hamster wheel.
That is exactly what it is. We essentially built a mathematical hamster wheel to trap the variable safely. This choice actively imports intrinsic compactness for mathematical safety.
So we didn't discover the wheel?
No, we didn't find this compactness in the corpus. We didn't discover that delta phi was a hamster wheel. We chose to construct U delta this way.
We built it ourselves.
We built the wheel and put delta phi inside it to make the canonical machinery work, completely bypassing the Susskind-Glogower elevator crash. It is a fully exponentiated phase operator.
Okay, this is brilliant. So we built a safe container for the phase. We chose to make it compact via this U delta operator.
Right.
Now that we have U delta successfully built and installed, we need to construct its conjugate partner, the action variable, the momentum side of the quantum coin.
Exactly.
And we need to figure out exactly where the quantum aspect, the actual physical h-bar, gets injected into this system.
Right. We need to define J delta. J delta is the leading order action-like conjugate variable. It is the partner to U delta.
Okay.
And this is the most perilous part of the paper. This is where we have to be incredibly painstakingly careful about the boundary between the corpus and the extension.
Listener, if you are multitasking, come back to me now. Pay close attention here. Because the math uses two different symbols that sound incredibly similar, but confusing them ruins the entire honesty claim of the theory. Remember that classical momentum we talked about at the very beginning of the deep dive? The momentum of the pendulum bob.
Oh, right.
That momentum used a coefficient called alpha effective. We said it was derived directly from the SRC sim corpus.
Right, alpha effective. We pictured it as the heavy brass dial that came permanently bolted to the machine by classical reality.
Yes, but our new quantum action variable, J delta, does not use the brass dial. It uses a completely new supplied normalization factor. It's called alpha delta.
Alpha delta. Okay. So alpha effective is the brass dial from the existing theory.
Right.
Alpha delta is, let's visualize it as a shiny new digital dial that we brought in a titanium briefcase, and we have deliberately taped it to the side of the clock. It is completely ours.
I love that visual.
Yeah.
A digital dial we brought in a briefcase, yes.
Yeah.
Alpha effective and alpha delta are completely different objects, serving completely different roles, and they must never be merged.
So they stay separate.
Completely separate. Alpha effective is classical inertia. Alpha delta is the quantum action scale.
So the paper never accidentally slips and replaces one with the other.
Never. That is the discipline. Enters by construction through the supplied alloys, which is not derived.
So Al is grounded now.
No. Alloys supplied. What physically fixes its value is open. The construction shows it can be introduced consistently, not what grounds it.
That is such a vital point. It is almost dizzying how honest that is. We are saying to the physics community, look, if you want to map this classical phase to quantum mechanics, you have to twist this new digital alpha-delta dial until Planck's constant appears.
You'll have to force it.
You have to tune it to h-bar. But we are simultaneously admitting that we have absolutely no idea what physical reality in the universe is turning that dial.
We don't. We don't know what grounds it in nature.
Yeah.
Admitting we don't know is precisely what makes the framework robust.
It's refreshing, really.
We've built the casing, we've installed the dial, but we explicitly state the dial is waiting for physical grounding. But here's the payoff. Once we supply that alpha-delta dial and we bring in h-bar through it, we can finally construct what the paper calls the root-2 canonical relation.
The root-2 backbone. After all this construction, what does that final quantum rule actually look like?
It is the mathematically safe global form commutator we built. It states that the commutator of our constructed action, J delta, and our hamster wheel operator, U delta, equals h bar times U delta.
And a commutator, just for a quick refresher, is just the mathematical way of measuring how much the order of operations matters,
Yeah,
right?
exactly.
Like putting on your socks then your shoes is different than putting on your shoes then your socks. The commutator measures that difference. In quantum mechanics, that difference is what creates uncertainty.
Spot on. And our root-2 commutator equation perfectly safely encapsulates that uncertainty. And just to reiterate, because it is the absolute core of the whole deep dive, it contains h-bar because we put it there.
We brought it in.
We smuggled it in via the alpha-delta digital dial. We did not measure it organically bubbling up from SRC Sim.
We brought it in the briefcase. Now, the paper calls this root 2. Does that mean there was a root 1?
Yes, the paper meticulously documents a root 1. Root 1 is the naive local approximation. It's the elevator without a floor.
Ah, the broken one.
The paper explicitly flags that root 1 is mathematically dangerous and is only valid for tiny, tiny semi-classical phase increments where you don't risk hitting the vacuum state. Root 2, the exponentiated U delta, the supplied J delta, is the actual mathematically safe backbone of the formal extension.
Okay, let's take a deep breath. We've hacked through the jungle. We have successfully built our canonical route.
We made it.
We've got our hamster wheel U delta, our quantum action J delta, our digital dial alpha delta, and our safe root 2 commutator. But as we've said over and over, an honest framework must be totally transparent about what it has deliberately set aside for later.
Always.
So let's review the boundary table. Let's look at the fire door.
It is a very stark, well-lit line. On the corpus side of the boundary, what the theory gives us, we have the Lagrangian SRC sim structure.
Right.
We have the quadratic kinetic term, we have the periodic readout of the sine function, and we have the classical brass dial, the alpha effective coefficient. That is the kinetic architecture, and it belongs completely to the theory.
And on the extension side, the scaffolding we built.
On the extension side, we have the exponentiated hamster wheel operator, U delta.
Right.
We have the supplied action scale, the digital dial, alpha delta.
Okay.
We have the constructed action variable, J delta. And we have the safe global root 2 canonical relation. The kinetic architecture belongs to the theory, but the quantum of action is entirely ours. We built it.
Now, earlier we mentioned something that we kind of left hanging. When we talked about the classical conjugate momentum, it had the brass dial alpha effective times velocity, but it also had a second part.
Oh, right.
It had chi, that velocity-dependent coupling term. But when we just built our quantum J delta, we just used our digital dial alpha delta and the phase velocity. We completely left chi out of the quantum blueprint. Can we just set chi to 0?
The paper sets chi aside for the leading order construction and flags full treatment as future work. It doesn't claim chi vanishes. It's set aside at this stage.
So it's still there in the physics. It's still a real effect. We just haven't built the quantum math complex enough to handle its interference yet.
Precisely. The fully coupled construction where J delta properly integrates the effects of chi without breaking the commutator is an explicit target for future work. It's a gated item. It is a known unknown.
And there are other gated items, too, other open work. We already discussed the biggest one, the grounding of alpha delta.
Right, the digital dial.
What physical force actually fixes its value is totally open. But there's another fascinating connection mentioned right near the end of the paper regarding an operator called FPAI.
Yes, FPSI, the recursive update operator. Within the broader ODTBT program that this paper sits inside, FPSI is the massive overarching operator that governs the recursive dynamics of the entire system.
It's the engine.
Yes, it's the engine that drives the universe forward step by step in this theory.
So wait, if J delta is our newly built quantum action variable that measures the quanta of phase, and FPI is the master engine driving the recursive phase updates, it feels like they should be intimately connected, right?
You'd think so.
Like, FPSI should logically be the thing generating the exact phase shifts that our J delta action variable measures. They should be two sides of the same coin.
It is a highly plausible future candidate for a deep connection. In a fully unified theory, they almost certainly would be connected. But again, the paper is utterly ruthless in its discipline here. FTI is only named as a plausible candidate. The connection is absolutely not derived.
It's just a hypothesis.
Exactly. To actually link them, you would have to mathematically prove that F-psi generates the exact canonical transformations we just built in our root 2 commutator. That mathematics has not been done yet.
So none of these massive implications, the coupling of chi, the grounding of the alpha-delta dial, the unification with the master F-tie operator, none of these are actually claimed to be solved in this addendum.
Correct. The sole singular claim of Addendum 24 is a disciplined route for treating delta phi canonically.
That's it.
That route is built as a formal extension. The seam between the classical corpus and the quantum scaffolding is left highly visible, and all open questions are clearly named and gated.
You know, sitting here looking at all of this, it brings us to the ultimate question for this deep dive. Why spend an entire theoretical paper, pages and pages of dense, rigorous mathematics, outlining what you aren't doing?
It seems counterintuitive.
It does. Historical deep dives into Susskind-Glogower, meticulous definitions of dials and operators, all this careful framing. Why does this incredible level of pedantry actually matter to physics?
Because a theoretical framework earns trust by being mathematically precise about what it hasn't done yet. Think about the current landscape of theoretical physics.
It's pretty wild.
As we said earlier, anyone can write a paper claiming they found a hidden quantum structure. They can play fast and loose with variables.
They can merge a classical coefficient like alpha effective with a quantum scale like alpha delta.
Yes. Pretend they're the same thing, sweep the Susskind-Glogower paradox under the rug, and announce a grand unified breakthrough to the press.
So can mirrors. Building a skyscraper on sand.
Exactly. The harder, infinitely more valuable thing to do is to draw a bright line in the sand. To stand in front of the scientific community and say, here is exactly what the theory gives us.
The workbench.
Here is exactly what we built on top. Here is the exact line between them. And here is a detailed, brutally honest list of what remains open.
That's real science.
The paper never blurs the two. It holds a strict discipline. Every single claim is tagged as either derived from the existing theory or constructed as a new extension.
So it never conflates the brass dial with the digital dial.
Never. It never pretends a periodic readout is an intrinsically compact hamster wheel.
It's the difference between selling someone a house and selling them a blueprint with a giant red circle around the empty plot where the house still needs to be built.
Yes. And that is what makes the work scalable. If you build a massive theory on a fudged assumption, eventually the whole thing collapses under its own weight when you try to apply it to a new, rigorous domain.
It falls apart.
But if you document every single assumption, every single supplied parameter, every single constructed operator, then future researchers know exactly where the load-bearing walls are.
They know what's safe.
They know what they can trust and what they need to reinforce.
So I want to turn to you, the listener. As you navigate the world, I want to leave you with a provocative thought to ponder. In the wider world of physics and science in general that you read about in the news every day, how many discoveries are actually just constructed mathematical extensions completely overlaid on a theory?
It's a great question.
How often do we mistake the scaffold that human beings brilliantly built for the fundamental building itself? It is something to think critically about the next time you encounter a grand, sweeping scientific claim.
You really have to look closely.
Were the gears in the clock actually quantum all along? Or did someone just sneak in a briefcase with a new dial, tape it to the side, and forget to tell you they put it there?
Distinguishing constructed from derived keeps the formalism honest as it scales.